And really, you come up with a few stock phrases every now and then. What is the point of doing this? And you can just see the teacher's face drop a little bit. Or, is this on the syllabus? Exam classes start to get closer. The teacher just feels like having a little bit of fun, maybe exploring the topic a little bit more in depth. Somebody puts up their hand and says, is this on the syllabus? And again, you can just see that the teacher's face drop and go, well, no. And then somebody will say, well, what is the point of doing this? And it's just like a self-repeating cycle. But really, the worst one in which you can say to wind the teacher up is, when am I ever going to do this in later life? And to be honest, I was a complete sucker for that question. Because I used to think about a topic and I would say, well, if you were going to become an accountant, then maybe when you were doing your accountancy, you might choose and I would pathetically try and justify what I was teaching you for when you were going to use it in later life. But I've got something to tell you, and that is that the vast majority of what you learn in maths you are never going to use again. Okay? Maths is not as useful as we make it out to be. Okay? It's about knowledge, it's about understanding, it's about enjoying the subject. And I've got another message for you. It's not just maths that is pretty useless. If you think about what you are learning in school, then actually, I have never used the fact that I understand conveyor bonding ever again. I have never used the fact that I learned how to form an oxbow lake ever again. I have never ever labelled a plant cell in my life. And just because I know about the 6 Ys of Henry VIII died, doesn't make me a better person. However, it does give me knowledge. And knowledge is incredibly important. And the more knowledge you gain at school, the better you will become as a person. So don't think that you have to use this stuff in later life for it to not be important in your development as people. Because I promise you, the number of people that will use trigonometry will be basically nobody in this room unless you become a maths teacher. So, really, what am I going to start by talking about today? Well, I'm going to teach you something so useless, so pointless, that the only thing you'll ever be able to use it for is just to have a little bit more knowledge. And what I'm going to be talking about is a concept that has been around for thousands and thousands of years, but no one has dared to touch it until the last 100, 150 years. And it's the concept of infinity. You know about infinity. You see infinity many, many times before. You look at recurring decimals and they go on infinitely. But have you ever actually thought about what the nature of infinity is and how it's used? There is no subject other than maths that actually genuinely uses infinity. Physics may talk about infinity, but actually a truly infinite number actually occurs really in mathematics because we enjoy to use it. And perhaps in theology, we don't talk about that at school. And so really, the two people might have like infinite heroes of the infinite story. The first one is George Cantor. George Cantor was around at the end of the 18th century, beginning of the 19th century, and he was the person who really did the pioneering work with infinity. He sent himself around. He sent himself completely mad. He ended up in an asylum for the last 10 years. Because as far as he was concerned, because he understood infinity, he saw the face of God. And once he saw the face of God, that was the end of it. He ended up in an asylum. He spent the next 15 years toying with an idea of proving it one week and disproving it the next week. And the other guy, the far chirpier chap, was somebody called David Hilbert. And David Hilbert and George Cantor were great friends. And basically, between them, they understood infinity and they began to explain actually what infinity is. And so what I'm going to do is I'm going to take one of George Hilbert's analogies and I'm just going to explain it to you in a way that Hilbert explained it. But for that, I'm going to need a straw hat because George Hilbert always wore a straw hat. And basically, Hilbert had this idea of a hotel, and it was called Hilbert's Hotel. The thing about Hilbert's Hotels is that Hilbert's Hotel was an infinite hotel. It had infinite rooms, but basically every single room was occupied. And then one day, Hilbert's in his hotel, and he's standing around, and he's feeling quite smart because he's making an infinite amount of money per night. And then suddenly, he hears the doorbell ring. And he thinks, well, hang on, who's going to have I don't have any rooms. And so Hilbert basically went to the door, and he went to find out who could be at the door, given that he had no rooms and there there was a sign at the front that said, no vacancies in the hotel. And so we went across to Hilbert, to the front of the door, and he had a look to see what was going on. And he saw that his rooms were completely full. This is room 8, room 7, and every single room was occupied. And then at the front, he saw somebody, and he went, what the hell are you doing? He says, well, this hotel's full. And this person basically said, well, hang on, I need a room for the night. And Hilbert said, you couldn't possibly have a room here. It's full. And they said, you must have a room. It's an infinite hotel. And so Hilbert thought about it. And then what he did was he basically, in his infinite loudspeaker, asked everybody, every single resident, to simply move up by one number. And so every single resident simply moved up, shifted up by one number. So 1 went to 2, 2 went to 3, 3 went to 4, and so on. And what did that mean? He then said to the guest, come on over, room 1 is free for you. And so actually what Hilbert did was he demonstrated that even though you had infinite occupancy, you could still make space for one more person. And then Hilbert was feeling pretty smug about this. And then he looked out from the front door, and basically, on the horizon, he saw there was a coach. It wasn't just any old coach, it was an infinite coach. And he saw the coach coming, well, it's fine, it's going to pass by a hotel. When actually it didn't pass by the hotel at all, the hotel pulled up in its infinite car park. And Hilbert was like, okay, what are we going to do here? And the first person came up, and he said, listen, I've got an infinite coaches. I've got an infinite number of people in the coach. Please maybe help me out. I need to be able to accommodate all these people. And I know this one, don't be ridiculous. You've got an infinite number of people, and I'm infinitely full. He said, there must be some way that you can do this. And Hilbert sat there for a few minutes, and he was looking at his infinitely full hotel. But he had a brainwave. And what he said was this, he said, okay, this is what I'm going to do. I'm going to ask every single resident to go into a room that is double their original room. Well, that meant that the person who was in room number 1 goes into 2. The room that was in room 2 goes into 4. The room that was in 3 goes into 6, and so on. And so they all basically moved into a room that was double their original room. So you can see what's happened here is that basically the person was in 1 goes into 2, 2 goes into 4, and so on. And actually, the people who were in 6, 7, 8, 9, 10, well, they would actually occupy the rooms of 12, 14, 16, 18, and 20. But look what's happened. Hilbert has actually managed to create an infinite number of spaces in his hotel. By doing that, he simply tells the person who's in seat number 1 to go into number 1, to room number 1. He tells the person who's in seat number 2 of the coach to go into room number 3. He tells the person that was in seat number 3 to go into room number 5, and so on. And so you can see that even though there was an infinite number of coaches, there was an infinite number of people, he managed to accommodate all of them in his hotel. And this happened on an infinite scale. Hilbert was feeling so smug, it was unbelievable. He was making an extremely large amount of money. And he thought, I'm going to call it a day. And then just as he was about to call it a day, he looked out on the horizon again. And on the horizon again, he couldn't believe what he'd seen. He'd basically seen something which was so extraordinary, he knew he was going to have to think about this. And just before I go on to that, I just want you to bear in mind one thing, that at the moment, in terms of the nature of infinity, what have I told you? I've told you that if you add 1 to infinity, you still get infinity. And actually, if you add an infinity to infinity, you still get infinity. We're beginning to understand the nature of infinity. But this doesn't exclude the problem I just had. I don't just see 1 coach. I don't just see 2 coaches. In fact, I see an infinite number of coaches headed towards Hilbert's hotel. An infinite number of coaches, and on each coach, there is an infinite number of people. And Hilbert gets this feeling of impending doom. He knows what's going to happen. And he thinks, how am I going to accommodate an infinite number of coaches with an infinite number of people in each coach into the hotel? And he thinks long and hard about this. And he thinks, I'm going to need to phone Canton for this one. And so he gives Canton a ring. And well, the answer to what happens comes tomorrow. Thank you. with the ideas and the concept of it, then actually the best place to start off is by thinking about number sets. Okay, number sets sound terribly, terribly boring. And I'm just going to introduce three of them to you. The first one is symbolized by the castanet illustration. And it just means the natural numbers. It is the most basic, infinite number set you have. It starts at 1, then to 2, 3, 4, and it goes up. And if you think about how big the size of that set, how many numbers are in that set, then it's obviously infinite. There's an infinite number of numbers in the natural numbers. And then we look at the second set. Okay? And this is the set of rational numbers. They're just fractions. Even in intro, you know what fractions are. You know how to reduce a fraction. You put a whole number on the top. You put a whole number on the bottom. You cancel them down if you can. And that is the set of rational numbers. It is all the fractions you could possibly write down. Every single fraction. How many fractions are in that number set? Well, there are infinite. And the final one we're going to look at is the real numbers. And so the real numbers expressed by R are every single number you could possibly write down as a decimal. Every single number. Whole numbers, rational numbers, things called irrational numbers. As long as you have a decimal point and you write, and you carry on writing, you have what's called the real numbers. How big is that set? How big are the real numbers? And then think about how big the real numbers are in comparison to the rational numbers, and how big the rational numbers are in comparison to the natural numbers. And it seems so obvious. They are all infinite sets. But the natural numbers must be smaller than the rational numbers, and the rational numbers, it stands to reason, must be smaller than the real numbers. And if you ask yourself that question, and you allow yourself to see how the answers unfold, then maybe you'll start to understand how infinity works. But we'll start off by just looking at the natural numbers. They're just the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what Cantor did, and we spoke about Cantor yesterday, is he came up with something brilliant. He said that if you have what's called a one-to-one correspondence, that means you have a number that corresponds to 1, another one that corresponds to 2, and another one that corresponds to 3, and then actually they are the same size of infinity. So here we've got the natural numbers, and here I've just written down the prime numbers. I don't even care if you know what the prime numbers are. Okay, actually I do care, but that's a lot of fun. For this, here I've got the prime numbers, 2, 5, 2, 5, 7, and so on. The point is that I can correspond the 2 to the 1, I can correspond the 3 to the 2, and so on. And I can correspond all of these. And what does it mean in maths? It means that they're the same size of infinity. You think there are less prime numbers than there are whole numbers. But that's not true. If you can make this correspondence, if you can simply label them up like that, and you can say, well, this number can go into 1, this can go into 2, then actually they're the same size of infinity. And once you start understanding that, you can start to understand what infinity is all about. And so what we've then got, it's a shame from zeros here, what we've then got is that actually the natural numbers have been allocated a size of infinity. And trust the Jews when they get involved when the numbers get big. Because here we've got, should be over here. Obviously, you know, Windows formatting didn't quite work. What we've got is the natural numbers, this infinity. Actually, infinities have size, and the natural numbers, because you can count them, because you can count the natural numbers, have been given the size out of fields. It is the smallest of the infinities, although the Jews still want to know even in the smallest of the infinities. So here we've actually got that a way of labeling, saying how big an infinity is. The natural numbers are the smallest. But what we really want to do is to get back to what I was talking about yesterday. And so I need to go back to my normal syllable. Because if you remember yesterday, I left you with this problem. There were these coaches. There was an infinite number of coaches. And an infinite number of coaches that came into Waterhill was Hotel. And in each coach, there was an infinite number of people. And Hill didn't know what to do. He didn't know how to accommodate all these people. So he gave the councillor a ring, and he said, okay, councillor, what the hell am I going to do? And actually, the councillor's just phoned back. And he's come up with a solution, which is brilliant. It is an absolutely genius solution. And what he said is this. He says, Hill, you both know it's an infinite car. What you need to do is this. Is you need to put a labeling system with coaches and seats. So people in coach 1, seat 1 go to that square there. People in coach 2, seat 1 there go to there. And he put an infinite grid onto his infinite car. And he started to get people to stand on the grid. And so what happened was, is that they then all stood onto the grid. So Mr. Strong stood in seat 1, coach 1. Mr. Unhappy, Mr. Uppity, stood in coach 2, seat 1. Mr. Afro stood in coach 3, seat 1, and so on. And everybody was happy, and everybody had things. Look at Mr. Tickle in coach 3, seat 5. Okay? They were all in a grid, a massive, infinite grid in their car park. It was brilliant. But so what? They've still got to get into the hotel. Why don't you then just go down this list and put the tell you who's going to the hotel, and then review and tell you going to go. What is the problem with doing that? Well, the problem is, if you tell everybody in that column to go into the hotel, you'll never get to the end. Remember, it's infinite, it doesn't stop. So this person, Mr. Talk, never actually gets to go into the hotel. So what do? Well, actually, you get them to go into the hotel in a particular order. And so all you do is this beautiful sort of zigzag sort of thing. You go down, you go up, you go across. And can you see, nobody actually has to walk an infinite distance. Everybody, in an infinite number of coaches, from an infinite number of people in the coaches, all gets to go into the hotel. And Mr. Strong gets to go into room 1, Mr. Unhappy into 2, Mr. Saul into 3, and so on, and everybody's getting into the hotel. Gilbert, along with the council, devised a way of getting an infinite number of people in an infinite number of coaches into his hotel. And they were incredibly smart. But the smugness doesn't even begin there, because how does this relate to anything to do with maths? Well, what you do is you get rid of the word coach, and you put in the word numerator. For those of you who don't quite remember, that's the top of the fraction. You get rid of seat, and you put in the denominator, the bottom of the fraction. You get rid of the mismatch, because Mr. Mary resists maths. You get rid of the numbers and the arrows, okay? And then it really starts to be fair. In this box here, you put 1 over 1. The numerator is 1, the denomination is 1. You didn't put in 2 over 1, where the numerator is 2 and the denomination is 1. And then you put in 1 over 2 into that space there, where the numerator is 1 and the denominator is 2. And you carry on doing this process, doing all these fractions into this grid instead of missing them. And this is the genius of it. Because then you do the same labeling pattern as you did with the missing them. But now you're doing this fraction. You don't worry about 2 over 2, because actually that's the same as 1. You then carry on, and you do the whole labeling pattern again. You've got 2 over 4, but that's the same as a half. 3 over 3 is the same as 1, 4 over 2 is the same as 2. And provided you just get rid of the repeats, what you can then do is you can then start to put these people into rooms. So 1 over 1, which is 1, goes into room 1, and you can see up there that actually in room 1 now goes value 1. And then in room 2 goes number 2. In room